My name's David Marticello, one of the creators of Ripple. Ripple is an app that enables you to track your water usage in real time and encourages better water usage habits. As drought becomes an ever-increasing problem in today's world, this is just the kind of app that is needed. Here you can see our test setup. We have a few branches, each containing a control valve and a flow meter. This setup can represent many different water devices in the home. Now we're going to see Jason Rotella, our architect and front-end engineer, walk us through the app.
What we have here is the physical modeling of an organization's water system. You'll notice here that there are not enough devices to represent all of the possible end uses of water in a given organization, be it a home or a business. However, we've modeled three particular use points. Could be, say, a shower, a sink, and possibly a dishwasher, for example, in a home. At the bottom of this model, this physical model, we actually have another device which is sourced not with the main source of water that goes into all of these other devices, but rather a reclamation source from this tank down here. This reclamation tank is fed by this parallel branch and controlled by this particular relay here. Now, for water devices which actually pull their source water from the reclamation tank, this concept will actually provide a benefit in terms of the end user experience. They'll get additional rewards, a higher quota that they're able to use, or other types of benefits that are important to them. And here we have the Arctic 10 board that was ordered for this contest. There's another Arctic 10 board that's being used here as well, since there are multiple participants' boards involved. The Arctic 10 is on the left, as you can see. We have a particle photon on the right-hand side, as you can see, attached to the breadboard. This could equally well have been an Arctic 5 or Arctic 1 chip as well. However, like I mentioned, we already have two Arctic 10 boards, so we didn't actually have one for the contest. However, the code that's running on here, which I'll describe in a moment, is not unique to this particular device. Anyway, now I'll describe about what we're looking at. So essentially, what we have here is, as you saw before, the physical system that was on the board that was described previously is here represented by these LEDs. The state of these is representing whether the water device is drawing water at this point in time. The number 1 device is the dishwasher in the home. The number 2 device is the sprinkler in the home, outside the home actually in this case. The 3rd device is the washer. The 4th device is the shower, and the 5th device is the sink. As you can see, most homes would have more water devices than what's shown here. However, and they would probably have multiple versions of the shower and the sink and so forth. But for the purposes of building a physical system, this is what we were able to implement economically. This LED is representing the state of the water reclamation tank pump that was described earlier when the physical system was described. Now I'll talk about the software a little bit and the connectivity to the solenoid operated valves as well as the flow meters that were in the physical system. So to operate the valves, which these LED states actually represent, that's done with the Arctic 10 board itself under the supervision of a custom emulation server that was written with the Go programming language. And this particular server communicates with mobile application, actually for everybody that is within the organization or within the home on their own phone. You'll see a representation of that later. So the WebSockets between this server that's running on this small module right here and those hybrid mobile applications is how the users actually interact with and get information about the state of their water system. Over here we have the particle photon, which is running Apsara's NATS messaging bus service. And it's essentially passing over Wi-Fi from here over to this Arctic 10 board the real-time water measurements from the flow meters that were shown in the physical implementation earlier. For devices which do not have a physical flow meter attached to them actually spinning and that are emulated devices, those particular devices can have a flow rate which is stored in the data structures of the emulation server running on this board here. Next, we'll take a look at the database server that this utilizes as well, which is running on the second Arctic 10 board. Previously, we looked at the Arctic 10 board that's running the applications server. This particular Arctic board, which is the second one that was referred to, is running a version of the RethinkDB database, actually 2 replicas of it. The information that's stored in here actually initializes the simulation and tracks all of its state regarding what people are allowed to do and not do, the rewards that they've signed up for, and any civic actions that they've decided to participate in. We'll talk about a lot of those features later when we do the user interface walkthrough. Here we're running the emulation server with the Arctic board as a target. Instead of emulating this, it will use the GPIOs on the board to control the valves. You just saw the server boot up, and now we have the web server, which actually is going to provide the facility that provides the mobile application to the end user, which you'll see in a moment. So here we're back at the emulation server, and you see the console. Now we're looking at the database. You see initiators, providers, and quotas. Initiators are the people. Providers are the water devices. Those quotas are what the folks have signed up for. Here we're refreshing the mobile application, noting in the console that after we open a WebSocket to organization 0 for user DAD, see in the beginning he is actually not an administrator of the water system. That'll change after we initialize it. So here we open a WebSocket to the server from the browser. Note it opened up. We open a listener on the browser so that it can talk to the web server. Now we initialize the people in the organization. The initializers. The initiators in this case, excuse me. You note here on both of these pages that there are no water devices shown to interact with. These pages will be populated with devices when we run the initialization. Here we have a page that shows how folks can collaborate. Now we'll initialize the people in the organization. You see the console of the server shows that that's done. Now once this is accomplished, if the person that's running the mobile application is an administrator of the water system, they will get a set of buttons unique from a standard user. They'll be shown here. You see we have init providers, we have shift personal quotas, turning off and on all devices, and now we're going to initialize all of the water devices in the home. You see in the console that that's going by, sending messages to the browser to initialize all that information. Now, if we go to these 2 pages we looked at previously, we now see we have water devices there with the current state, which is a bit redundant at permissive. And now we have water devices and non-water devices, even a dryer here, that we can collaborate around to do collaborative chores in the home. Any of these devices that use water can be preempted, including the dishwasher, by a civic action which requires water consumption somewhere else in the community, such as a firefighting incident or possibly a watering of a Little League ball field. Here we're going through requesting and using the dishwasher with the requisite messages shown in the console that in fact the commands were executed. The result of this is that the valves that you saw in the system running water in the earlier part of the video actually are going to be passing water at this point, and the usage will be tracked with the water flow meters applied toward the quotas that we talked about earlier.